you should be in the midst or done with completing this sheet, which will, in our discussion next time we get together, will lead to some important understandings about the nature of electricity and how electrified objects interact with one another. Here is your hook, which will really not be satisfied until we've had that discussion tomorrow, but Benjamin Franklin was one of the preeminent scientists of his day, and his field of study, for which he earned his greatest fame, was electricity. The famous flying the kite in the electrical storm, which was not just a lark. He was trying to find out if the electricity, which was up in the air during an electrical storm, was the same stuff as the kind of electricity he was making in his laboratory. But he made a very important contribution to the nomenclature of electricity, and we will get to that tomorrow. Please fill out the sheet and sort of the basis for what we're talking about in this lecture, but we'll do the best we can without having that sheet completed. So when we get together, after we finish that discussion of that sheet, we're going to do an experiment involving an electroscope. This is one form of electroscope. The fancier ones have glass panels over the front, and inside there's often gold foil or gold leaf. But this is a very hardy and robust, and it will serve our purposes well. We need to know the parts of it, and then you are going to do a lab in which you will think very deeply about how those parts behave. It consists of a can, and it's very important that that be made of metal, that it be a conductor, because, and here it is again here, it is a fact that we will learn later that when you have a metal enclosure, there is no field inside of that metal enclosure that arises from outside. That charges have electrical fields around them, but none of that field will go through this metal enclosure, and that's why it is there, to shield from external fields. There can be fields inside, but they will then only arise from charged objects inside, nothing from outside. In particular, this metal plate that we refer to as the top. That plate, if it is charged, will have a field around it, but that field will not affect things inside. Then there is the post, this vertical, you can see it here in shiny metal, making a sort of a, I don't know what you call that shape, a Z. And then there is this straw, which is here it's in yellow here. Right where the straw rests on the post, there is a pin, and it is a metal pin. The straw also has been coated with graphite. Metal of this can, metal of this top, metal of the post, metal of the pin, and the graphite. All of them are conductors. And what we understand that to mean is that charge, whatever charge is, moves freely in a conductor. The opposite of a conductor is an insulator, and insulators do not allow movement. When we talk about an insulator, when we're talking about heat, we don't allow the heat to move. That's what an insulator does. Stops the movement. All right, back to this can, and I'm sorry to give you all these details without something to work with, but I hope you can absorb them. So we have a conductor here, and a conductor in that straight pin that goes through the post, and a conductor here in the post. So charge can move freely from the straw through the pin and onto the post. At the top of the post there is a screw here, and it goes up to the top. So there is a conductive pathway from the top to the post and onto the straw. It is important in the design that there is a nylon bushing here that separates this can from the other parts, which are all conductive. So charge will not flow to or from the can with regards to the rest, but charge will move freely over the top post straw. I think that's all I need to say. You will note in the course of doing the lab that we will talk about the straw either being repelled, pushed into this horizontal or to some angle, or the straw being here against the post or close to the post, which we would call relaxed. But you will notice that we do not say that the straw is attracted to the post. And the importance of that will come up as we do our discussion at the beginning of the period next time. Okay. So, some more details. Suppose this is a conductor, and it is neutral. That is to say, it is without charge. But what that means to be without charge is that there are equal amounts of both kinds of charge. That there will be protons and electrons, both of which carry charge, and equal amounts of both kinds here inside of this metal. That's what it means to be neutral. Now, suppose I bring another charged object, this one is positively charged, up here close to this. There will be, as indicated by the pink here, a field around this positive charge. Actually a field that does go away, but we'll get into that another lecture. What would that do to this piece of metal? Well, the negative charges here in the metal are attracted to that positive, and the positive charges here in the metal are repelled by it, and this orange thing is a conductor. So if there's a force on them, they will accelerate. And what's going to happen? We got trouble, people. Come on, you. Get up to the front. There we go. It worked so well when you weren't looking. All right. So, there we go again. That this thing was neutral, but if you put it in an external field, then the charges will rearrange. And one end of this object will be negative, and the other end will be positive because of the field from this thing. It'll push them around. But if we were to take this charged thing away and its field, would a conductor stay like this? No. The negative charges attract the positive attract the negative. They're in a conductor, so they would feel that field from these two, and they would move. And they would only stop moving when, again, the charge was so distributed that there were no positive or negative parts of this object. So in the absence of an external field, a conductor is going to have the same charge everywhere. it could be that this thing is charged negatively, but it would be equally negatively charged everywhere. But in the presence of an external field, the charges will rearrange. Okay, well, remember that this can is shielding the inside from external fields. But if I bring something charged close to the top, let's let it be something positive that I bring up there. Here we'll go with pink. If I bring something positive here close to the top, then that will it will attract electrons, and it will pull them to the near side of the top, leaving the bottom of the top short of electrons. Now, that's going to make a field. This field from that pink thing caused this rearrangement, but this field here, although it cannot reach through the can, will talk through this conductive pathway. And it will pull, this positive here at the top will pull electrons off of straw and post, causing electrons to go up to the top, leaving a shortage of electrons down here. And so although there's no external field talking inside, these things become short of electrons because through this conductive pathway they've been pulled up to the top by that positive charge. And I think you can imagine what these two would do to one another and how the straw would be pushed or pulled. That is how the electroscope is going to behave. And that is sort of the way you need to talk about it as you do the lab. As you do this lab, it is very important that you only talk about electrons moving. You just take that as a fact from Mr. Houghton, that electrons are little and they're able to move around. Protons are big, they are tied into the nucleus, and they do not. Unless you are in a electrified gas or liquid, the electrons do not really move. They may have forces on them, but they are so big and clunky they don't move. It is the electrons that move. So, in your discussion for this lab, only talk about electrons moving. That we made this point here, that a conductor, in the absence of an external field, take away that external field again, cannot have different charges at different places because it's a conductor. Charge can move. They will attract one another, and so they will move, and they will only stop moving when there's no longer a difference. Boom. This metal can will shield you from external fields, so do not talk about the top or some charged strip that you held out here affecting what's inside. The straw, like everything else inside, does not feel fields from the top. It can communicate its charges up to the top, but it will not feel fields from the top. Again, very important that the straw is either deflected, pushed away, or it comes back, that is, it is relaxed. It's never attracted, and I want you to worry about why is it never attracted, and talk about it with your lab partners. If in the course of doing the lab, and this is a detail, if it doesn't make any sense, just let it go, but it may come to be that you will see two things happen. That as you bring something up towards the top, the straw will first relax and then as you bring it closer to the top, the straw will pop up again. So the straw starts out deflected. As you bring it up, it first relaxes and then deflects again. If you see that happen, what you should put in the lab is that first thing it did. But it would be well for you to see if you can explain the second thing that it did. Thank you. It's going to be an excellent lab. It's going to work you very hard, but I expect you to rise to it and do a beautiful job. See you tomorrow.